Last episode, we put together this basic resonant low-pass filter. And although it's still missing its most important attribute, namely being voltage controllable, it already has a lot of boxes checked, at least in my book. There's one feature that I've dodged talking about last episode though, and that is how we can modify this design to work as a high-pass filter. Because ideally, I'd like to implement a mode switch in the end, making the filter type changeable on the fly. To get there, we'll first make our lives a little easier by breaking this design down and then taking a look at one individual filter stage again. So on the left side here, we have our simple single-stage active low-pass. The input signal goes in here, squeezes through the resistor, fills up the capacitor, and then we get a filtered output from our buffer over here. Simple stuff. Now, if we want to convert this into a high-pass, all we need to do is switch these two connections. Because if this resistor is connected to ground and our input is applied to the capacitor here, we've essentially created an active version of the passive high pass we built in the first episode. The input signal pushes against the capacitor, the excess charge escapes through the resistor, and we get a filtered output from our buffer. But applying this idea to our resonant two-pole design is sadly not that easy. There's a rather glaring issue. This first filtering stage's capacitor is already connected to the filter's output to create the resonance. And we can't really mess with that without also messing with that resonance. So connecting our input signal right here is pretty much out if we don't want to heavily alter the overall filter design. And since we'd like to switch the filter type on the fly, heavy alterations are quite impractical here. So what other options do we have? There's really just one left, connecting our input signal to this second capacitor and grounding the low-pass input over here, effectively turning our filter into a single-pole resonant high-pass. How does this work? Well, the high-pass section itself should be clear by now. But what about the resonance? To figure this out, let's once again walk through the filtering process step by step. As an input signal, we'll use a simple square wave as usual. So at some point, the input voltage will jump from 0 to, say, 5 volts. Now initially, those 5 volts will be transferred wholly to this node as they push right through the capacitor. This will kick off an instant chain reaction, where we'll see a rapid rise in voltage here, and in response also here. This spike will then push through this capacitor and is pitted against the input signal through this op-amp. For a brief moment, this will block the excess charge here from escaping through this resistor, like it normally would when this point is ground connected. So instead of an almost instant drop at the filter's output, we'll see the voltage linger around the peak for a little bit. But of course, this can't really last. While this node here is being squeezed by two pushing forces, this node over here only sees one voltage coming from down here. So the excess charge will quickly begin to drain out through this resistor. This in turn will make the voltage here drop and allow for a current to flow through this resistor. From here, it's basically the same story as with the low-pass configuration. We'll see the same cascading effect kick in as the drop in voltage is propagated from here through here and back to our first filtering stage, which will pull the voltage here even lower, allowing for more current to flow through this resistor. Eventually, the filter's output drops below 0 volts, which kicks off the familiar over and undershooting behavior. Because since the voltage here is now in the negatives, a current will start flowing from ground through this resistor and into the capacitor, raising the voltage here and thus reversing the cascading effect's direction. After some time, the output will stabilize at 0 volts. That is, until the input signal changes and the whole process repeats. Now, of course, doing it this way requires a rather hefty trade-off. By using the first stage solely for creating resonance, our filter will behave like a simple single-pole high-pass. This means a loss of precision, since the roll-off gets less steep. But I think this is tolerable, and so did the people at Korg when they designed the MS-20 filter section. Because that MS-20's high-pass filter is constructed almost exactly like this. But before we make a hasty judgment regarding the performance, let's take to the breadboard and hear how this sounds. All we have to do is connect the filter's low-pass input to ground and then send the buffered input signal to this capacitor here. Since this is such a small change, doing this with a switch later on should be rather easy. And here's what that sounds like. First, without resonance. Next, here's 50% resonance. And here's about 90%. For my purposes, I'd say this is perfectly serviceable. With that out of the way, let's talk about voltage control. Traditionally, for a synthesizer's filter, that means moving the cutoff point not by hand, like we've done up until now, but with an electric signal. This way, we're able to automate filter movement with other modules like LFOs, envelopes, and sequencers. But as I mentioned before, voltage control is actually one of the trickiest parts of synthesizer circuit design, at least in my opinion. And that's because most of the time, your best bet is looking for a device that can convert a voltage into something like a resistance. In our filters case here, we would need to replace these two resistors with such a device. Then, by varying the resistance values using a voltage, we'd be able to move the cutoff point. The problem is, though, that resistors are pretty damn great at what they do, which makes it hard to find an adequate replacement. For one, resistors work the same no matter which way you orient them. A current flowing this way will see the same resistance as a current flowing this way, which is very important for our use case since audio signals, by definition, oscillate, and so they alternate between pushing and pulling current through here constantly. Also, resistors are what we call linear devices, which means that if you double the voltage here, the current flowing through the resistor will double as well. This has its limits, of course. At some point, it's going to go up in flames. But for the most part, we don't have to worry about the amplitude of our input signal here. Resistors are going to behave reliably linear in virtually all scenarios. Both of those features are very important because if resistors were nonlinear or asymmetrical, the oscillation passing through our filter would be severely distorted. Okay, but what options do we actually have for replacing our resistors? Well, there's a few that come to mind. If you've watched my DIY VCO series, you might say, why not use a transistor? After all, we were able to switch out the drain resistor in our oscillator core for a run-of-the-mill NPN transistor. In that scenario, we could then control the oscillator's pitch with a voltage. And while that did work rather well, it was also a very favorable situation for the transistor. Because for the most part, a transistor like the one we used is neither a symmetrical nor a linear device. But in this particular application, unlike in our filter design, it doesn't really need to be. Now, for brevity's sake, and in order not to derail this video completely, we'll just have to leave it at that. I will take a closer look at transistor-based voltage control in a future episode, but for now, we'll focus on easier to handle alternatives. And probably the easiest is actually a kind of crude and curious device called the Vactrol. Vactrols are essentially just two run-of-the-mill components slapped together, an LED and a light-dependent resistor. We'll call them LDRs from now on. The idea here is this. LDRs, as their name implies, are resistors whose resistance value changes with the amount of light that shines onto them. If they're completely in the dark, their resistance value will be very high. And if they're in a very bright environment, it will be very low. Conveniently, we can control the brightness of an LED by pushing more or less current through it. So if we take an LDR and an LED, bring them very close together, and then seal them off from ambient light, we'd have a device that effectively converts a current into a resistance. Best of all, an LDR behaves pretty much like a normal resistor, save for the light dependency part, which means that it's symmetrical as well as linear, allowing us to plop it into our circuit without having to alter the design much. This sounds like pretty much the perfect solution to our problem. So why don't all synth modules use Vactrols all the time? Well, as you might have guessed, there are a few significant drawbacks. First of all, ready-made professionally built Vactrols are relatively rare and expensive. It's just not something that most electronics stores normally stock. Second, LDRs react rather sluggish to a change in brightness. Now, in the upper light intensity range, you can get response times of around 10 milliseconds. But when going from bright to very dark, it can take up to several seconds until the resistance value is settled. And even with a 10 milliseconds response time, audio rate modulation is mostly out of the picture. Vactrols can't really respond to signals faster than 100 Hz. Third, and most importantly, every Vactrol behaves a little differently because of mechanical and component-specific variations. The angle at which the LED is pointed at the LDR, the exact distance between the two, differences in LED brightness at identical current levels, differences in LDR resistance values at identical brightness levels. These factors all play a role in Vactrol performance. Why is this important? Well, if you think back to episode 1, you'll remember that a multi-stage filter's performance depends on the individual stages being set to the same cutoff frequency. The more those frequencies diverge, the less defined the filter slope will become. And so it's desirable to have identical resistances here and here, since these determine the individual stages' cutoff frequencies. But if we replace these two resistors with Vactrols, we can't really count on their effective resistances to ever be identical. Since every Vactrol behaves somewhat differently, we'll get different resistances here and here for a given control current. Now, you might be inclined to try and match your Vactrols to minimize the problem, but doing that is rather uneconomical given the fact that Vactrols are pretty expensive. So if there's all these drawbacks, why use Vactrols at all? Well, two things. First, since they're so easy to use in our design, it's a convenient way to get going when you're just starting out. Sure, the end result might be a little shoddy, but it will definitely be somewhat usable. And second, we don't really have to hunt down professionally made Vactrols in some obscure web shop. If you just buy some LEDs alongside some LDRs, which are both readily available, you can quite easily make your own homemade Vactrols. Obviously, those will perform even worse than the proper ones. But since we're already compromising on filter precision and mostly just want to kick this whole voltage control thing off, I think it's perfectly okay to compromise a bit more. Okay, so if you're on board with this, we'll now have 3 questions to answer. What kind of LED should we use? What resistance range should our LDRs cover? And how are we going to encapsulate them? For the LEDs, I've found some conflicting information online. Some people say that green or yellow LEDs work best, others swear on red or white ones, and of course there's people that say it doesn't matter at all. So I will just go with the standard 5mm red LEDs. For the LDRs, I'm using ones with a decent range. These go from around 300 to around 10 megaohms. Now for the final and crucial problem. How do we actually make a Vactrol out of these components? I think the most popular DIY approach is to use heat shrink tubing. But some time ago, I came across a video by a channel called Minijack, who used something called FIMO to create a solid plastic enclosure. Since I always wanted to try this, I figured now would be the perfect opportunity. You can buy this stuff at most arts and crafts stores here in Germany, and I guess anywhere else too. It works like this. When you take it out of the packaging, it will be soft and malleable. But once you put it in an oven at 110 degrees Celsius for half an hour, it will harden into solid plastic. So all we need to do is find a way to lock the LED and LDR in place facing each other. I'm using my breadboard here. And then form two equally big flat pieces of FIMO to create the enclosure. We need to make sure it's airtight so that no ambient light can get in. To help us differentiate the LED from the LDR connectors, I'll carve symbols into the FIMO right here. Repeat the process, and then both proto-Vactrols go into the oven at 110 degrees Celsius. And here's what they look like after 30 minutes. The enclosure is now completely solid, and so our homemade Vactrols are ready to use. Before we drop them into our circuit, we'll have to think about how we're going to drive the internal LEDs though. The thing about LEDs is that they burn out really quickly if you push more current through them than they can handle. So if we simply connect our input voltage straight to the Vactrol without running it through a current limiting resistor first, the LED would die instantly. Because red 5mm LEDs like the ones we used are rated for a maximum current of 20 milliamps, while my synthesizer's power supply can and will push out 1 full amp given the opportunity. That's 1000 milliamps, enough to fry about 40 LEDs at once. How do we prevent that? Easy. We just have to do a bit of math. Since my power supply's positive rail sits at plus 12 volts, we can assume that to be the maximum voltage we'll have to deal with. So if at 12 volts, the current going through our LED should be 20 milliamps, so 0.02 amps, we can calculate the required resistance value using Ohm's law. Resistance is voltage divided by current. So 12 volts divided by 0.02 amps equals 600 ohms. Knowing that, we can set up the most primitive version of Vactrol-based voltage control, which is really just an audio jack connected to the Vactrol's LEDs through 600 ohm resistors. The Vactrol's LDRs then simply replace the stereo potentiometer we used previously. One thing to look out for is that while for the LDRs the orientation does not matter, the LEDs will only work if you connect the short leg to ground and the long leg to the control voltage. So I'll simply remove the stereo potentiometer and plug in our Vactrols. Connect the internal LEDs to ground and to the control voltage socket, and we should be ready to test this. For demonstrative purposes, I'll add another LED here and connect it to the CV input as well. As a control signal, I'm using a triangle wave LFO. Right now, its amplitude is turned all the way down, so our filter's output is quiet and the LED is not lighting up. But watch what happens as I turn up the LFO. The filter's cutoff frequency starts going up and down smoothly. Now, if I switch the LFO's waveform to a square, you'll notice that on the way up, that frequency jumps almost instantaneously, but going down, it's only slowly trailing off. This, like I said before, is due to the fact that it takes an LDR quite a long time to adjust, going from a bright to a dark environment. Unfortunately, this means that with this setup, the filter is always going to behave really sluggish, no matter how quick and precise the control voltage tries to close it. But apart from this limitation, there's another problem with our design. There's no way of dialing in a specific base cutoff frequency. So right now, when there's no control voltage applied, the filter will always be completely closed. This is rather impractical, and that's why pretty much all filters have a cutoff frequency knob in addition to the control voltage input. Thankfully, adding such a knob to our design is pretty straightforward. Instead of sending the control voltage directly to our Vactrols, we'll mix in an offset voltage first. We'll get that offset voltage from a potentiometer, set up as a variable voltage divider. Just like last episode when we divided down the feedback for the filter resonance. But this time, we're dividing down the positive supply rail so that our offset can be any voltage between 0 and 12 volts. Now, the basic concept for the voltage mixing is this. You have your fluctuating control voltage here, and you have a set offset voltage here. Then you connect them using resistors, whose values determine the relationship between the two signals in the resulting mix. If both resistors are of the same value, that resulting mix will always be the average of the two input signals. So if our CV input is 5 volts and our offset is 10 volts, the resulting voltage here will sit at 7.5 volts. You could of course alter the relation between the two inputs by using unequal resistance values. But for now, we'll keep it simple and use two 100k ohm resistors. Before we can send our voltage mix to the Vactrols though, we'll have to buffer it with an op-amp. That's because these resistors will strongly limit the amount of current flowing in from our input signals. This means that the voltage at this point is really fickle. As long as we're not drawing any current from here, it will be stable. But connect just a small load and the voltage will drop dramatically because there's not enough current coming in to sustain it. With a simple non-inverting op-amp buffer, we can fix this problem by taking that fickle voltage and providing a much more stable copy over here. That copy can then easily power our two Vactrols and even the additional LED we threw in to visualize the filter state. Since our first TL074 is already working to capacity, I'll set up another one over here and configure one of the op-amps as a buffer. Next, I'll make a variable voltage divider using a 100k ohm potentiometer. Send the CV and the offset voltage to our buffer using 100k ohm resistors, hook the buffer's output up to our Vactrols plus the demo LED, and we're all set. Okay, so to check out what the offset voltage does to the filter's cutoff frequency, I'll disconnect the LFO for now. Next, let's try sweeping that potentiometer. As you can hear, the filter's range is kind of squished together at the beginning of the full sweep. So there's a huge dead zone at the high end of the cutoff frequency spectrum. What's up with that? Well, as you'll hopefully remember, a filtering stage's cutoff frequency is determined by the relation between the resistance and the capacitance value, because it's all about how long it takes for the capacitor to be filled up and drained. The slower that process, the lower the cutoff frequency, and vice versa. Now, in our design, we keep the capacitor values the same while varying the resistance. So we can visualize the relation between resistance and cutoff frequency as a simple two-dimensional graph. And here's what that looks like for the 10 nanofarad capacitors we're using right now. As you can see, the audible frequencies between 20 and 20 kilohertz are mapped to resistance values ranging from 800 to 800 kilo ohms. So ideally, you'd want our Vactrol's effective resistance ranges to cover this area exactly. Now, I said earlier that the LDRs I used in my Vactrols cover a range from 300 to 10 mega ohms. So surely, had I used a different model, our filter would work just fine now, right? Actually, no. The problem is that the relation between brightness and resistance for an LDR is extremely nonlinear. I'm not going to pretend that I can go into mathematic detail here, because I really can't. So you'll have to accept an extreme simplification. And that simplification goes something like this. At the lower end of the brightness spectrum, an LDR will react extremely sensitive to the tiniest change. In my tests with the Vactrols I built, even turning the LEDs on just barely will make the resistance drop from 10 mega ohms to around 40 kilo ohms. Increasing the brightness from there though, that extreme sensitivity calms down gradually, and so the actual really usable resistance range of our Vactrols is somewhere between those 40 kilo ohms and 300 ohms. Keep in mind that the Vactrol still does not behave linearly in this area. It will jump much quicker from here to here than from here to here. which is why there's such a huge dead zone in our potentiometer sweep. After turning it up just a slight bit, and thereby making the LED glow just faintly, the cutoff frequency will jump to more than 1 kHz. Okay, so what can we do about it? Well, there's multiple things you could do, but I'll just pick the easiest one since it's already quite effective. Pushing this curve to the left by using bigger capacitors in our filter stages. Because for a given resistance, an increase in capacitance means a decrease in cutoff frequency, since filling and draining the cap will take longer. In my tests, replacing the 10 with 33 nanofarad capacitors gave me some decent results. As you can see, the Vactrol's usable range now covers a solid chunk of the audible frequency range. We also get a nice side effect. Since most of the action is now happening while the LED is brightly lit, our Vactrol's response times are overall significantly improved. Mind you, this is still far from perfect. For one, we're cutting off everything above 15 kHz, so our filter can never be completely open. And more crucially, the relation between control voltage and cutoff frequency is still going to be pretty skewed. Normally, that relation should be exponential, so that a linear increase in control voltage results in an exponential increase in filter cutoff frequency. We'll talk more about why in a future episode, but to achieve that with our Vactrols, we'd need to dive a bit deeper. And frankly, I'm not fond enough of the Vactrol approach to be motivated to do that. So let's just see how we fare with bigger capacitors. All we have to do is remove these 10 nanofarad capacitors and replace them with 33 nanofarad ones. Let's first try the cutoff sweep again. Yeah, I'd say that's an okay range. So I guess it's time to bring in a sequencer plus an envelope. For now, I'll give you the pure output from the filter, without using a VCA and without any effects. And here's how it sounds with a VCA and some effects. And finally, configure it as a high pass. So this is where I'll leave it for our basic Vactrol VCF. In the next few episodes, we'll explore other, more precise and reliable approaches to voltage control. In the meantime, you might be interested in checking out my Patreon, because if you've enjoyed this video and would like to support the channel, you can do that there. Anyways, thanks for watching and until next time.